for about a gravitational wave observatory, which is the observatory which, for the first time in the history of mankind, detected experimentally the presence of gravitational waves in 2015, as you know. So we are very honored to have a research scholar from IIT Bombay today with us. His name is Nirban Bose, and he is presently working on with the astrophysics and the gravity group in IIT Bombay. Before this, in 2017, he did a master's in science again at IIT Bombay in physics. He has a Bachelor of Science from the University of Calcutta from 2014. So at present, he's working on trying to find out the different parameters of the merging bodies which create gravitational waves. So just by looking at the signal, we can tell a lot about what's happening up there. What's the size of this body, whether it's a neutron star, which is a very heavy star, uh, or whether it's a black hole which comes together and forms a bigger black hole. So just by looking at the signal that you receive on the LIGO observatory or the detector as it's called, you can tell about what's the size of these black holes, how far they are from each other, what their masses are, and all of this requires complex physics and technology and a lot of engineering that goes on in the background. So we will hear now from Nirvan Bose. Nirvan, please.
Thank you very much for the introduction, Evan. So, I'm going to talk about the basics of gravitational waves. I'll begin with a very sort of basic introduction on how gravity came into the picture with the help of Newton, and then gradually Einstein came into picture, and how he proposed general relativity. I'll not go on to the details since this is a general public talk, and I'll focus on basics of gravitational astronomy, which is now at present, I think, is the most booming field in the area of physics research. So let's get started. So this picture is familiar with most of you all. This is Newton, and we all know the story that while he was sitting in a park, an apple fell, well, not on his head, but fell downwards. From there, he got the idea that why is this apple falling downwards? It may have gone upwards. It looks like very simple, simplistic idea, but actually it's not. So this idea gave birth to the idea of gravity. So Newton proposed that there is some kind of force which make bodies which have mass fall downwards. Well, he couldn't do experiments outside the Earth, but while sitting on the Earth, he gauged the situation and made the inference that there is some kind of force which makes the apple fall downwards. This force, he named it gravity. Uh, so, as I told you, so if you define gravity, what is gravity? Gravity is some sort of force which attracts objects toward. Remember that gravity is always attractive. Well, electromagnetic force can also be repulsive. If you have two same charges, they can repel each other. While if you have two opposite charges, they always attract each other. This is the main difference between gravity and any electromagnetic force. So, in this case, the pull is indeed because of gravity, but you cannot qualitatively, leave it at the point of qualitative definition. You have to quantify it. So Newton gave a very simplistic equation of gravity. Let us suppose if you have two objects of masses m1 and m2, uh, and they are separated by a distance of r. So the attractive force between them will, will be given as g into m1 into m2 divided by r square. So this is the magnitude of the force. So any two bodies which are separated by a distance r and has mass m1 m2 will be attracted towards each other by this amount of force. So this was the definition of, not definition actually, the quantification of gravity up to a certain, I think 18th or 19th century, before Albert Einstein came into picture. So what Einstein proposed is that the idea of gravity, Einstein's idea of gravity is not exactly similar to that of Newton's. But indeed, Newton's idea of gravity was a simplification of Einstein's idea of gravity. What Einstein wanted to do is to propose a more general theory of gravity. So he proposed something called general theory of relativity. Now, what was the drawback of Newton's theory? Was it wrong? No, of course it was not wrong. It was valid. But Newton's theory of gravity made certain simplistic assumptions about the real systems, which Einstein uh, made it more general. Well, the two drawbacks of Einstein's theory, or to put it in other words, the two modifications which Einstein proposed compared to Newton's theory is, first, in Newton's theory, there was no upper limit on the speed of any object, which said that any object can travel at infinite amount of speed. But of course, today we know that it's not correct. So what Einstein did is, firstly, to propose an upper limit on the speed, which said that no object in the universe can travel at a speed greater than the speed of light, which is 3 into 10 to the power 8 meters per second. Now, this was the first thing. The second most important thing is that in Newton's theory, space and time were separable. They were treated as different entities. You can find the position of an object after some time t, where you clearly distinguish between space and time. Einstein said that actually space and time are not separable entities. He treated these space and time on the same footing. That means these were equivalent quantities. You cannot separate space and time. So actually what we mean by space today, or what the general notion about space is that when we talk about space, we think it like some sort of universe where all the planets and heavenly bodies are there, moving and doing whatever crazy thing they're doing. But actually these are combinations of space and time. You can visualize it as the as some rubber sheet where both and time, space and time are sort of clumped together. And when you make a change in this sheet by placing some heavy ball on it, you actually change both the space and time of the sheet. So something like this. So imagine, so this is the green thing is the sheet which I am talking about. See, this is a sort of rubber sheet. So each point on this sheet, in Newton's gravity, in each point on this sheet used to be denoted by three spatial coordinates: x, y, and z. Suppose we consider this room. If I stand here to sort of identify my position, I'll require three coordinates. One is the x-axis, which you have to first fix the origin, of course. If you fix the origin, one quantity you need is the x-axis, which is this. One quantity you need is the y-axis, which is this, and one quantity you need is the z-axis, this. And you have to separate the time, like now it is 11:35. So you specify these three coordinates and you specify the time separately. But in Einstein's general theory of relativity, each point is denoted by four or higher dimensional specified coordinates, minimum four or higher dimensional coordinates. So if you place some heavy object which has mass in this rubber sheet, the rubber sheet gets bent. That means there is change in the spatial coordinates as well as in time. Okay. So, yeah. So this was the equation given by Einstein in his general theory of relativity. This is believed to be, up till now, one of the most general equations in physics. So you don't, these are called tensors. You don't have to go into details. What are these? Uh, you can understand it in this way that these are something that specifies physical quantities in higher dimensions. Okay, these are the indices of the tensors. So the basic idea of this equation is that the left hand side g mu nu encodes the geometrical information of the system. Okay, and the right hand side t mu nu encodes the information about how much matter is present in the system. So let's suppose what is the mass of the system, or what kind of system, what kind of matter is present in it, in this ball, is present in this T mu nu. This information is present in this T mu nu. Whereas how much this ball would curve the rubber sheet geometrically, what will be the geometrical shape of the rubber sheet due to this ball, that information is encoded in the G mu nu. So this equation actually connects matter with geometry. So Einstein's main aim of this general relativity is that it connects matter with geometry, whereas Newton's gravity didn't have this generalization. This is where Einstein's general relativity is distinct from Newton's relativity. Now, as soon as Einstein proposed this general relativity, there were several outcomes of this general relativity, or several solutions of this equation. One of these important solutions is black holes. Now, I'm sure that most of you in this auditorium have heard of what are black holes. So, what happens is when stars, you see stars in the sky. So, when these stars run out of their, so in these stars, there are constant burning of hydrogen. Okay. Now, when the star, it may so happen that after, say, millions of years, this hydrogen gets burnt out. Okay. When it burns out, so it is left to helium. Now, in this way, all the gases and all the fuels which burn out actually goes on exhausting the fuel capacity of the star. So, what happens after one fine morning? This star bursts. The outer core of the star bursts. This is called supernova explosion. Why supernova? So what does supernova mean? Supernova means death of a star. When supernova explosion happens, the outer core of the star just goes away, boom, and tremendous amount of energy is released. So the energy is so much high that at that particular point of time, it can outshine the entire universe. So much of energy. So the if the outer core is burnt away, shell is burnt away, it is left to the inner core of the star. The inner core of the star is extremely compact. Say 10 times the mass of the sun is sort of contracted into some 3 kilometer radius. So imagine if you take a spoonful of matter, how much heavy that it will be. These are called black holes. So black hole is the outcome of a dead star. Now, one important feature of black hole is that the gravitational attraction of a black hole is infinite. No one can escape. If you come near to a black hole, you cannot escape the gravitational pull of the black hole. You will get inside the black hole and you will never be able to come out. This is the important feature of black hole. What is the other important feature? Now, from Einstein's general relativity, you can tell if a black hole is sitting inside it. Now, imagine a mass of, let's say, 10 times the mass of the sun is sitting inside that rubber sheet. It will automatically bend the rubber sheet and shrink the rubber sheet. So, imagine if a heavy mass is there, this is a rubber sheet, if a heavy mass is there, you keep a heavy mass there, and if I try to walk around that heavy mass, automatically I will fall towards that heavy mass because it bends the space-time around it. This is what exactly happens with black hole. Anything that wants to pass near the black hole, it gets bent. And if you go too much close to the black hole, you fall inside it. This is called singularity. Now, there are some important properties of this black hole, which I'll try to explain in easy language. The first thing is, of course, I told you this rubber sheet will get bent because of this black hole. There's another sort of quantity or phenomena which you can define. I think it's quantity. It's called the event horizon. It's the boundary of the black hole. So, what do you mean by event horizon? So, imagine it this way, that this room is a black hole. So these walls are the boundary of the black hole. So if you come inside this black hole, you cannot go outside of this room forever, for eternity. So these boundaries define the event horizon of the black hole, from where you cannot escape the gravitational attraction of the black hole. Now, photon sphere. What is a photon sphere? Now, the photon sphere is the radius or the distance up to which, I mean below which, if you come, you will get bent. So imagine it in terms of light. Since light is massless, so light is composed of many small particles, or I should say the quanta of light. By quanta, I mean the small particles which the physical quantity is composed of. They are composed of photons. They are massless. Okay. So if these photons try to pass near the black hole, they will get bent. Now there is a distance up to which this phenomena is exhibited. That radius is known as photon sphere. So if you go beyond the photon sphere, light will not get bent, because the gravitational reach of the photons, the gravitational reach of the black holes for the photons is not strong enough to bend the light. But if it enters the photon sphere, light will get bent. This is the property of the photon sphere. Now, another important outcome of the general relativity is what the main gist of the talk today is. It's called gravitational waves. And I'm sure many of you have heard of gravitational waves because it fetched the Nobel Prize in 2017, and I'm proud to say that there are there is a good amount of Indian contribution in that work, and many Indian scientists, I think you all should be aware of, since we are doing research in India. So it's important to understand for all of you the contribution of Indian scientists in the world science. So the Nobel Prize, which was won, actually had many Indian contributions, and if you follow it regularly, you'll understand that India is a leading country in gravitational wave research. So, anyways, gravitational waves are important predictions of Einstein's general theory of relativity. So, what are actually gravitational waves? So, just for a moment, if you go back to a few minutes earlier where I mentioned, so always I keep on giving this analogy of this rubber sheet because it's indeed helpful. So, if you place a heavy body in the rubber sheet, it bends the rubber sheet. Now, this rubber sheet is the space-time rubber sheet. So, actually, if you place a heavy body, it bends the space-time around it. So, if you have two, imagine heavy balls. In this case, the balls are black holes. So, 10 to the power 30 kg is the mass of the sun. If you go 10 times beyond that or 20 times beyond that, imagine the magnitude of the mass and the amount it curves the space-time. So, if you have two black holes orbiting each other, that means they are just going around each other. So both of them curves the space-time around them. Okay. And as they curve the space-time around them, they lose energy. That loss in energy propagates through the curved space-time in the form of gravitational waves. So if the two heavy bodies are there and they're orbiting around each other and the space-time sheet is getting curved and the energy is getting lost, so the troughs and trenches in the rubber sheet will propagate away from where they are actually orbiting. That propagation, that ripples, those are called ripples. those ripples carry away the energy lost by the orbiting system in the form of gravitational waves. So these are basically oscillations in the space-time that propagate, that carry the energy, the lost energy of the system. Another important feature is the gravitational waves travel at the speed of light, which is 3 × 10⁸ meter per second. This, well, there are theories which sort of object this fact. Uh, they say that exactly it is not similar to the speed of light, but more or less you can consider it similar. At least according to general relativity, they are similar to the speed of light. Now, another important property of gravitational waves is that